In this video, this is a basic introduction to moments. We're going to explain what a moment is and how we calculate a moment. The definition of a moment is its turning effect of a force about a point. In this little example here, it's easier to close the door if you push the door at point A than it is at point B. And that's because A is further away from the hinges, and the hinges are the points of turning. It's easier to undo a nut using a longer handled spanner, and that's because the force being applied is further away from the nut, which would be the point of turning. So we can see that the distance away from the point of turning is important in a moment. And that's the basis of Archimedes saying, "Give me the place to stand and I shall move the earth." He was basically saying if you could stand far enough away from the earth with a long enough lever, you could apply a force which would move the earth. So what we would need is a very, very long distance here. Okay, because we would be rotating this lever about this point here. This would be called a fulcrum. So we'd be rotating this lever about this fulcrum or point of turning. And if this part of the lever here was long enough, we'd be able to move the earth. So to calculate a moment, the moment of a force is the size of the force multiplied by the perpendicular distance from the line of action of the force to the point of turning. And we'll explain with examples a little bit more what we mean by this phrase, perpendicular distance from the line of action of the force to the point of turning. The unit of measurement is the Newton meter, Newton the standard measurement of force, and meter the standard measurement of distance. So it's a Newton meter. In the example of the long-handled spanner, if the spanner handle is 0.2 meters long and you apply a 10 Newton force at the end, then the turning effect of this force is 10 times 0.2, and that's 2 Newton meters. Sometimes when we're presented with a force, we need to find the perpendicular, and sometimes it's not easy to see exactly where the perpendicular is. So here's how I'll show you how to find the perpendicular. So suppose P is the point we are taking moments about, and this is the line of action of the force. So remember, we want the perpendicular from this line of action to the point P. If we place a ruler on our force such that this measurement here, which is measuring 7 centimeters as we can see, that little line there runs along the line of action of the force. What that must mean is the edge of the ruler, which is always perpendicular to these lines. It must be that the edge of the ruler is now perpendicular to this blue force. So it's perpendicular to the line of action of the force. So now what we want to do is to slide our ruler up the force until the edge of the ruler passes through point P, like this. So we can see now that the line of action of the force still runs over that 7 centimeter marking, which means this edge is at 90 degrees to the force, and now the line of action, or the perpendicular, passes through the point P. So this is the distance that we want. We mark that distance in, and then using SOHCAHTOA, we find that that red broken line is 5 sine 60, and so the turning effect of the 6 Newton force is the 6 newtons, which is the size of the force, times by the perpendicular distance, which is 5 sine 60. And that works out as 15 root 3, and the units are Newton meters. So here's an example taken from the textbook. We're trying to find the result of these three forces about the point P. Well, the easiest force to start with is the 6 Newton force, because that's acting vertically downwards. So we've got automatically the line of action of the force, and then that is at 90 degrees to the line of action, and it passes through the point P. So this 3 meters is the perpendicular distance from the line of action from the force to the point P. That means, and it's turning anti-clockwise, and so the moment is 6 newtons times 3 meters, which is 18 Newton meters. For the 5 Newton force, we want the line of action, which is perpendicular from the line of action of the force to the point P. So that is a clockwise turning effect, so that's a clockwise moment. We place our ruler so that this is in line with the 5 Newton force, and therefore the edge is perpendicular to the line of action of the force. We can see now it's passing through point P. So we mark on the distance, and that distance is 4 sine 80, which means the total clockwise moment from that 5 Newton force is 5 newtons times 4 sine 80, and that works out as 19.69, etc. Newton meters. There's one more force, and that's the 4 Newton force. Once again, we want the perpendicular from the line of action of the force, which passes through the point P. So we put our ruler, it's a anti-clockwise moment. We put our ruler such that this line here is in line with the force, which means the edge of the ruler is at 90 degrees to the line of action of the force. And so we slide our ruler until it passes through point P. Okay, note this marking on the ruler is still along the line of action of the force. That's key. Therefore, the edge is at 90 degrees to the line of action of the force, and it's passing through point P. So now we can mark on the distance, and using SOHCAHTOA, that's 3 sine 40, which means the turning effect of the 4 Newton force is 4 newtons times 3 sine 40, 7.71. So now when we put all the three forces together, the anti-clockwise moments were 18 from the 6 Newton force plus the 7.71. The clockwise moment is 19.69. So overall, the anti-clockwise moment is bigger than the clockwise moment. So the resultant turning effect is equal to 6.02 Newton meters anti-clockwise. In example 5, let's separate out the two forces to find the resultant turning effect of these two forces. So the 7 Newton force, we want the line of action, which is of the force, the perpendicular to that line of action to point P. So first of all, it's a clockwise moment, and the line of action, there it is. Let's mark it on, and we find that that broken red line is 8 sine 25. So the turning effect is 7 newtons times 8 sine 25, 23.666, etc. Newton meters. For the 4 Newton force, as you can see, that's turning anti-clockwise, so that's an anti-clockwise moment. The line of action of the force for the 4 newtons, we want the perpendicular to that line of action, which passes through the point P. You mark it in, and that's 8 sine 35. So the turning effect, or the moment of the 4 Newton force, is 4 times 8 sine 35, and that's 18.35 Newton meters. So overall, two forces, we have 18.35 anti-clockwise, 23.66 clockwise. So the resultant is 5.31 Newton meters clockwise. And now if you turn to exercise 4B on page 74, you'll find some questions which practice exactly what we've just done in this video. Best wishes, hope it goes well.